Hi everyone, and good morning, good afternoon, everyone. Yeah, during this first part of this fair chat set, I will show you the realization of the short circuit analysis of the PM motor. It will be a three-phase short circuit, but it will be the principle. It will be the same principle for other type of the short circuit. This is the summary about this first part. We start by quick introduction about the aim or the goal of this short circuit analysis, why we do this short circuit analysis, why not. And the second step, it will be the creation of the geometry. As you can see from the pictures, I will use SimLab instead of Flux to create this geometry, to create this circuit, to control the switches in the circuit. For the circuit, it will be the same steps or the same workflow that we follow in case of the Flux. Creation of geometry, the mesh, the physics, the circuit. Once this is done, the last step is the solving. You have your solving scenario, and after this, when you solve your project, you do the post-processing. Let's start by small introduction about the short circuit analysis, why we do this analysis and why not. When we speak about the short circuit analysis, three-phase short circuit or one-phase, different type of the short circuit. In this case, this leads to get height value of the current. And when we speak about height value of the current, behind we speak about the losses, particularly the Joule losses in this case. And height value of the Joule losses, this leads to get height temperature in our motor, and this can lead to the damage the motor. Example, breakdown of the insulation, as you can see from these pictures. Now, for the short circuit analysis, this can allows us, the first one, to fix the dimensioning constraint of the motor, particularly the copper temperature and the insulation classes of the motor, because there is some limitation, some temperature limitation that we do not exceed, else we will damage the motor. The second point is the demagnetization risk, particularly for the PM for the permanent magnet motor. Now we'll start on this slide. We'll see the creation of the geometry using SimLab. As you can see here, I started using a step file, but you have the possibility also to create your own geometry inside SimLab using the sketcher. In my case, I use a step import. As you can see here, I managed to import my step file in SimLab. The second step when we do the import of the step is the merge of the different part of the motor. Like this, it will be more clear when we have the stator yoke, the rotor yoke, the magnets, the air gap, the rotating air gap, the shaft, the wedge, and the coils. This is what we can see from the second picture. As a second step is the match of device. As you know, currently with SimLab, there is different possibilities to do the match of your motor. But the more adequate for in the case of the electrical motors is to use motor match. As you can see here from this picture, there is 3 parts. For each part, there is a specific part of the motor that you will match. We start by the stator. You can put the match size of the element that you have inside the stator. And as you can see here, for the stator, you have the stator faces. You should select all the stator faces. And also you can do the number of the repetition depending on the periodicity and the number of parts that you represent for your motor. It will be the same principle also for the air gap region. You will select the air gap face region in this part, and also you put the match size. The last part is the rotor faces. The same principle also. As you can see from this future motor match, the aim or the goal is to allow you to control the quality of your match in different part. If on the different part of your motor, if you want to refine, for example, in the air gap, you need only to act on the air gap region. In this case, you can decrease the match size. In our case, for this analysis, I used this type of the match for the motor. Now, the third step is the creation of the solution. Once you have imported your device, you have created geometry, the match, you will switch to creation of the physics. For this physics, we start by the solution. In this case, we use a magnetic transient analysis, magnetic transient application. The principle also, you select all the bodies, the different part of your motor. You remember when we have merged, there is a coils, magnet, stator, rotor, all this part you will select it as a bodies. From this one, in this case, we use a 2D model. You put the depth of the domain. You will select the control parameter depending if you use position of the time. You select also, you put the final time. In this case, depending on the number of the steps, on the number of periods, sorry, that you want to realize in your solving scenario. For example, in this case, it will take 6 or 7 periods. Then I should compute it as a function of this final time as function of the number of periods. The last factor or parameter is the time increment. This is also you compute it as function of the frequency, the number of points by for each period. Now we have managed to create the application transient. Now the second step for the physics is the boundary condition. We start from the infinite box. It's really very easy. You click on infinite box. You will get this windows. You can modify the name of this region if you want. You select the type of the infinite box that you will use, and also you will put the dimension of your infinite box, inner radius and outer radius. The second boundary condition is the periodicity. In our case, we will not represent the full geometry. We will represent only one part of the geometry. You click on this icon, you will get this window. You put the name of your periodicity. You select the type of the periodicity. Currently, you have linear or rotational. In our case, it will be rotational periodicity. And the last point is the physical aspect. You will select it will be you present one pole or two pole or three poles. It depends on the need. In our case, it will be odd. We have represented only one pole. Now we stay in the physics. The third step is the magnet orientation and the motion. For the magnet orientation, stay always in the physics. You will see also you go also in the magnet. You select magnet orientation. You will get the name here. You put the name of this orientation. You select the bodies. In our case, we have two magnets. I show you only for one magnet, but it will be the same principle for the magnet number 2. You see here, you select the magnet orientation. It will be unidirectional, and you click on define modify orientation. You will get this windows, and from this windows you will select in which axis or the nodes that you will use, and also the offset axis. Once this is done, you validate, and you get this new window. As you can see here also from this window, you have the possibility to select the demagnetization. I will not speak about it. My colleague Charishma will, in the second part of this fair chat, will give you some more details about the demagnetization effect. Then you validate. You will do the same thing for the second. Magnet for the orientation. The second point is the motion. In this case, also there is icon in which you will click. This window will be opened. You put the name of this motion, rotation, or depend on your needs, and you select. In this case, you select only the bodies in which you will apply. In which we have a rotation. And here, for example, also you select the motion type. You have translation or rotation. In our case, it will be a rotation. And here for the third part, you will select which axis it will be this rotation. You click on define modify direction, and you select Z axis and also the offset axis here. For the last part, you will select the type of the kinematic that you will use. In our case, it will be an imposed speed. And here, this is the initial position of the rotor. You define it initially, or you have it with previous computation. And this is the speed for this imposed speed. Beware here about the unit. It is not RPM. It will be radian by second. Now, the other part that I want to show you also here in this creation of this motor is the parameterization. As you know here, currently I use only physical parameters to control the switches and also the time, the speed, all these parameters. But you have the possibility also, if you want to create geometrical parameters using the sketcher. And from this table, this is all the parameters that I created. You click here, you go to the SimLab, you say create if you want to create a new, I'll say a new parameter, or if you have predefined parameters that you have created also previously as TXT or CSV file, you have the possibility also to import it in SimLab. The other information that I want to share with you also, as you can see here, there is a possibility to make a connection between all these parameters. As you can see, for example, the period, I can create it as function of the frequency, the current, the formula that I have for the current sources. As you can see also, this depends on the different on other parameters. The goal or the aim here is to say that there is a possibility to make a connection or relationship between all these parameters. Now, the last point is the circuit. From SimLab also, there is a possibility to create your own circuit depending on the different component or different element that you want to use in your circuit. You can go directly to the circuit designer, and from this circuit designer, you will select the element or the component that you want to put in circuit. In this case, we have current sources, you have the switches that we use to control the current in different phases, you have coil conductors, and also you have the inductance. As you can see also for these switches and the current sources, we have used the parameters that I defined previously that we have seen in the previous slide. Like this, if you want, for example, to modify the maximum current, you will not edit again, edit the current sources, modify the value here. You can do it directly from the parameters that we have defined previously. The same thing also for the for the switches here. You can see here I use only 2 parameters, but if you want to do it also for the time, you can do it. You have the period here, the parameter t that I defined previously, and also the final duration or the final period for the signal. Now, in the end, before solving your project, you can see here, you go to this angle, and you can see here, this is the different steps that we have followed to create the geometry. You have here the settings to see which initialization that you use in your motor. By default, there is an initialization proposed by SimLab, but you have the possibility to modify or change this initialization. You have also here this for the load and concurrent. You can see here the application that we have created, the magnet orientation, the boundary condition for periodicity, infinite box, and also you have the motion. Now, once this is done, you have created your model. Now it is ready to solve. You go to the results, you click on the results, you click update. And when you click on update, this means that you will run the solving of your project. The new feature that I want also show you during this Fire chat set is the possibility to see the evolution, live view of the plot during solving, or the evolution of your curves during the solving. You don't need really to wait the end of the solving and check the results and see if the results that you get are correct or no. As you can see from this picture, if you see, for example, some wrong behavior or some wrong shape of your curves, the current, in my case, I displayed the current and the torque. I can check both curves and see, for example, if really I meet or I can manage to reach the maximum current that I created before or no. From this curve, I can see, oh, my simulation is correct. I can wait the end of the simulation, or I say, oh, I will stop it because there's something wrong in my simulation or in definition of the physics of my physics. Then I need to stop the solving. I don't need to wait to the end of the solving. I will check again my physics and run again the simulation. Now, once this is done, the first thing our project is solved. The first thing that we will see is the ISO value of the flux density. This gives us an idea about the maximum flux density that we can manage or can reach with this motor. And also here you have the possibility to display and plot some curves. You can directly from this from results. This is the different possibilities of the post-processing. You can draw some curves. You can select plot, and here from you click on curves, and you will have access to this curves. You select the different curves that you want: the torque, the voltage, the current, the power, all these curves. This is an example of the results that we get from for this short circuit test. As you can see here, initially we have a normal working, if I can say this. We feed or supply with our motor with a normal working. for one period. After this period, there is a three-phase short circuit. According to the command that we use in our switches, we say from this time we can start the short circuit effect. As you can see here, we have an unbalanced current, and you have also some peaks of the current for the rest of the period. We see the same behavior also on the shape of the torque curve. As you can see here, initially we have around, I think, 400 Newton meter as the average value of the torque, and starting from this point where we have started using the short circuit, we see that we get some wrong shape of the torque. Yeah, just before I want to show you the model, and the model directly in SimLab. You see here, this is the model, and if I edit, for example, the current sources here, you see here I use the parameter that I have defined previously. The same thing also for the switches. I used all the parameters here, particularly for the on and off state resistance, but it will be the same principle also if you want to use the period here. You can put directly the parameter that we have created previously here, the period, this one, inside this circuit. For the resistance also, it will be the same principle. In this case, I used values, but you have the possibility also to define your resistance here and put it directly the value here. And initially, if you want to modify it, you can do it directly from your parameter. Yeah, this is about the first part of this fire chat. As you can see here, I managed to realize my three-phase short circuit analysis using SimLab 2025. There is also the switches that I used inside this circuit, and this switches allows me to control the moment, or the moment where I say I will start my short circuit. We can see from the results also that we displayed the current and the torque, but you can see also the voltage and other performances. You can see that there is really a short circuit effect starting from a given value of the period. As a next step, I will let my colleague Sharishma to present you this the demagnetization effect, according also to the short circuit analysis. One additional thing or information: this is a three-phase short circuit, but you have the possibility also to do the other type of the short circuit.